A very good day to Miss Sophia and whoever shall be watching this video. Today, me and my groupmate shall be presenting on the applications of differentiation in real-life scenarios and its importance. Our group consists of Alia Arissa Binti Yusaini, Noguchi Shunji, Skandharaj Bharathi anak lelaki Punithanathan, Lei Wutt Yee, and Yap Kai Ren.
First, what is differentiation? In simple words, it is a tool we use to study how one quantity changes with respect to another. In real life, we use it to find maximum and minimum values. For example, companies can minimize their costs or maximize their profit by choosing the best size, shape, or amount of material. Differentiation is also used to calculate rates of change, such as speed in physics of the growth rate of a business or an industry, because it helps us both analyze change and optimize results. Differentiation is very powerful method for decision making and problem solving in many different fields. In our presentation, we will show you some of these applications.
Before we start solving any mathematical problem, we must first try to understand what the question is asking. As the question states, a factory is designing a rectangular container as shown in the figure below with an open top with a volume of 16 meters cubed. The container will be used in logistics and manufacturing industry for storing components. One side of the rectangular base, L, is required to be 4 meters long. The material used for the base costs 8 ringgit per square meter, whilst the material used for the sides costs 2 ringgit per square meter. So now, before we start answering questions A, B, and C, by determining the dimensions of the container so that the container will be at minimum cost, we need to first break down the boxes into their individual faces. As shown on this slide, the box breaks down into 5 faces since the top is open. There will be 2 short faces and 3 longer faces. Now we can find the area for all the faces, which will help us to firstly solve for question A. For the 2 short sides, on the square face, the equation of the section is 2 multiply width multiply height. The expression will result in 2WH. The expression of the longer sides is 2 multiply height multiply length will result in 2HL. The final expression for the longer sides will be 8H. The last expression before we start answering the question will be for the base, 4 multiply width resulting in 4W.
The volume of the rectangular container is 16 meter cube. We know that the volume of a cuboid is length times width times height, and the question has provided us that the length is equals to 4. For the first step, we need to find variable of h. We have to do this by substituting the value of L equals to 4 into the volume equation. This will result us in getting h equals to 4 over W. For the second step, we need to find equation of total cost. To do this, we need to separate the question into 2 parts to make the calculation easier: cost of base and cost of sides. To find cost of base, we need to times 8 with 4W because the base cost Rm 8 per square meter. For cost of sides, we need to times 2 with 8H plus 2WH because side cost Rm 2 per square meter. To find the total cost, we need to sum up the cost of base and cost of sides. The total cost equation is 32W plus 16H plus 4WH. The third step that we need to do is substituting H equals to 4 over W into the total cost equation. Total cost equation to be 32W plus 64 over W plus 16. Fourth crucial step that we need to focus on is differentiate and solve for W. Let the total cost equation be C so that the differentiation calculation will be much easier. We have to let the derivative of the total cost equation to be 0 so that we can find the stationary points. We got W equals to plus minus Z2. We have to ignore the value of negative Z2 because it is impossible for us to get negative values for width. Still need to determine whether W equals to Z2 is really the minimum width or not. We have to perform the second order derivative of total cost equation. The equation will be 1 to 8 over W cubed. We need to substitute W equals to Z2 into the equation. We managed to get 32 Z2, which is more than 0. This has proven that W equals to Z2 is really the minimum width. Finally, we can find the value of height by substituting W equals to Z2 into the H equation. The minimum value for height would be 2 Z2. Question B asks us to calculate the minimum cost. We need to substitute these values into the total cost equation. Minimum cost to manufacture the rectangular container is 106 ringgit and 50 cents.
Before we move on to question C, let's understand how dimensions affect the price. For example, let's take a measurement of 10 meters and substitute it into a length L. The column chart here shows that when we recalculate the minimum total cost equation with a length of 10 meters, the price actually increases drastically compared to the price of its original length. The same thing applies for the width as well. The price increases compared to its original price. However, when the height is 10 meters, the increase in price does not increase as much as the other two measurements and is much lower than them. This goes to show that a rectangular container at a taller height costs less than a rectangular container that is longer or wider. This is actually because the height is the only dimension not affected by the base cost. Now that we've gone through the calculation path, let's talk about why mathematical optimization actually matters in industrial design. In industries, companies don't just guess what size or what shape a product should be. They rely on mathematical equations to make smarter choices. And this helps designers figure out the most efficient way to create something by testing different ideas using mathematical models. This means they can spot problems early and choose designs that work better and cost less. For example, optimization helps save materials, which directly increases profit because less money is spent on unnecessary resources. It also cuts down on waste, making the whole process more environmentally friendly. Time is another big factor at play here, as companies can manufacture products faster and avoid delays, which reduces overall cost. Mathematical optimization also helps ensure that whatever is being designed is structurally stable and safe. And one of the biggest advantages is being able to visualize the final product clearly before it's made. This reduces the chance of mistakes and helps teams create designs that meet technical requirements. Overall, it makes the whole design process smoother, smarter, and more reliable.
Now, what are the applications of mathematical optimization in industry? Well, its first application is that it helps to increase efficiency. This is because it helps to find the minimum material for a fixed volume, like we did just now in the question. This is helpful, for example, if a candy manufacturer has to create a box that can hold a certain volume of candy, but with no fixed shape. Mathematical optimization can then help him to minimize the amount of material used for the same amount of volume. Besides that, it also provides optimal dimensions for strength. This is because when you change a dimension, not only do you change the size of a container, you also change other factors, such as compressive and tensile strength. With mathematical optimization, it helps you to get all the benefits of these changed dimensions while also negating the downsides. Besides that, it also makes parts smaller and easier to form. This can help to save the environment because it helps to also reduce the creation of oversized materials. The other application is cost control. This is because mathematical optimization helps us to minimize material use, leading to higher profit margins. Besides that, it also reduces waste in manufacturing, helping to save the environment one step at a time. After that, It also supports optimal production levels and pricing, helping to keep new customers and drive growth. Finally, it also helps to improve allocation of resources and budget. As with the budget saves with resources, you can allocate it to different sectors of marketing. Now, the other two applications of mathematical optimization include time management and market demands. In the case of time management, smaller, more optimized dimensions help to shorten production time. This is because there is less cutting and forming needed, as more optimized dimensions can be cut and formed in one go. This helps to improve workflow and machine utilization and save costs for a producer over the long run, as they need to utilize the machine less and less and over less extended periods of time. Finally, the last application of mathematical optimization is market demands. This can be said because mathematical optimization helps to support innovation and problem solving as it uses derivatives to minimize error, such as data science and robotics. Besides that, it also helps to create cheaper, more optimized products. And these products, obviously, lead to higher customer demand and drive new growth in the company. All that is to say that mathematical optimization in industry helps to enable high speed and efficient production, balances costs, performance, and stability, provides clean visualization of optimal designs, and increases competitiveness in manufacturing. Thank you for listening to our presentation. We hope you have a wonderful rest of your day.